Okay, so let's start. The internet has been quite unstable here. It might get disconnected. If so, we will continue the lecture on Wednesday, but let's do as much as possible today. So we are going to discuss the different and the discriminant of a finite separable extension of P fields, right? Remember, P is a prime number, and the P field will usually be denoted K, right? So, but for the time being, let K be any field. And let E be a finite dimensional vector space over K, right? So that's the subject of linear algebra. And let's have a linear mapping from E to itself. Then I expect you to be familiar with this notion of the trace of this linear mapping U, trace of U, which is supposed to be an element of the field, of the base field K. So one way of defining the trace is to say that you choose a basis of the vector space E, you write down the matrix of the endomorphism U, and you take the sum of the diagonal entries of this matrix. Of course, one has to show that this sum is independent of the basis that you have chosen. And that turns out to be the case. So for every matrix or every endomorphism, in fact, we have defined a trace, and thus we get a linear map, and thus we get a map from the endomorphisms of E to the base field K. And this map turns out to be a linear map itself, okay? So that's a very basic concept. Now, instead of having a finite dimensional vector space, suppose I have a finite extension. Then I can consider it as a vector space, and I'll get the ring of endomorphisms here. And there's a mapping from the extension L to this ring of endomorphisms, which is not just K-linear, but it's actually a homomorphism of K algebras. So what is the mapping? It takes an element A of my field L to the endomorphisms of the vector space L, which takes a vector X to A times X. It's sometimes called left translation or left multiplication by A. So left multiplication by A is a map from L to L, and it's a k-linear map, right? Can you hear me, Debashish?
Yes, sir. Yes, sir. Hello, sir.
Can you hear me?
Yes, sir.
Who signed me out of this? I mean, it's very strange, but anyway, if you can continue to hear me, then we'll just continue.
Yeah,
Okay.
we can hear.
Fine, but that's not a good idea that, anyway. So now from what we have is a algebra homomorphism from L to the algebra of k endomorphisms of the vector space L. And from this, we have the trace map, which is the linear map to K. So the composite is what I'll call S L over K. So that's the S L over K of A is a trace of gamma A, where gamma A is this mapping taking x to A times x. Okay? So, so this turns out to be a linear map from L to K linear map. And I'm not going to prove it, but if you are at all familiar with the notions of separability, then one shows that this map, this trace map, is surjective, which is the same as saying that it's non-zero, because this is one-dimensional, right? This is one-dimensional. So for a linear map to be surjective, it's the same as being non-zero. And that condition is equivalent to the extension L over K being separable. Okay, so here is one way of understanding separability, that the trace map is not the zero map. An extension L over K is separable if and only if the trace L over K is not the zero map. Now, for example, if K has characteristic 0, then everything is automatically separable, and one should be able to see why the trace map is non-zero. In fact, it's non-zero because the trace of the element 1 in L is going to be equal to the degree of L over K. So it's non-zero, right? So that is the trace map. And one of the basic properties of this trace map is that if I have a tower of extensions, so K is a field, L is a finite extension of K, and M is a finite extension of L, then I can talk about the trace from L to K and the trace from M to L, and also, of course, the trace from M to K, all the way from M down to K. And it's easy to verify that the trace from M to K is obtained as the composite of the traces from M to L and from L to K. Okay, so this is a generality. It has nothing to do with P fields. It's a part of field theory of fields, right? Now, to the mix, till now, K was just an arbitrary field. Now I'm actually introducing a ring of which K is the field of fractions. So A is an integral ring and K is its field of fractions, and L is a finite separable extension as before. Then of course this L can of course be viewed as a module, and I can talk about submodules of A submodules of L. So an A lattice in L is a submodule of L, sub A module, which is of the form AE1 dot 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 AEN, it should be, where E1 to EN is a K basis of L. So what is happening is I have A here inside L, inside K, sorry, and L is a finite extension. Then I have a basis E1 to En. It's a K basis of L. Now, so there are certain elements, just think of them as certain elements and take the A submodule generated by these n elements, E1 up to En. Such a thing is going to be called an A lattice in L. An A lattice in L is a sub-A module generated by a K basis of L. Okay, so that's my definition. It's lambda is an A lattice if it is of the form AE1 plus AE2 all the way up to AEN, where E1 to EN is a K basis of L. Now, if I have a lattice lambda, then there's something called the complementary lattice. Okay, so before I introduce what it is, let me say that till now we were thinking of this S L over K as a K linear map, right? But what I can do is L is after all a field. So I have this map from L cross L to L, which takes x comma y to the product xy. And then I can apply the trace S L over K to get down to K. So this whole thing is obviously a bilinear, is a K bilinear map, because it's just enough to check that this is K bilinear, and that is part of the definition of an extension. So the first thing here is K bilinear, and this thing is K linear, so the composite is K bilinear. Now I have a lattice, and I have this K bilinear map S L over K. So it's x comma y going to S L over K of xy. So I can take the orthogonal with respect to this bilinear map. The orthogonal of this lattice is going to be denoted lambda star, the star here. So the formal definition is a set of all x in L such that the trace of the trace S L over K of x times lambda is another lattice, is contained in the ring of integers A. It's not the ring of integers, it's just the special subring of K with which I have fixed. So I'm working with a field K and a subring A of K. Then I have the notion of an A lattice in any finite extension L. And I have the notion of an A lattice and the notion of a complementary lattice with respect to the trace bilinear form. And what one can check is, so if the lattice lambda is given like this, where E1 to En is a K basis of L, then this complementary lattice is the sum of the dual basis. So if you have a basis of a vector space and you have a bilinear form, so it should be actually a symmetric and non-degenerate. Then what you get is a dual basis, right? So basically, if you have a basis of vector space, you get a basis of the dual space. And if you have a symmetric bilinear form, which is non-degenerate, then you get an isomorphism of your vector space with the dual vector space. So you can get the dual basis back to the original vector space. So you get a second basis in the vector space. And that second basis will generate a lattice. And that lattice is the complementary lattice. Okay? So it's a fairly simple idea. Now, let's forget about these arbitrary fields and rings. Let us come back to our P field K. And I'll take the ring inside this K to be OK, the ring of integers, as it is called, of the field K, right? If you're thinking of K with a valuation, then this consists of all X and K whose valuation is positive, right? And the lattice I will take to be OL. OL is an OK lattice in L. L is a finite separable extension of K. Over here it's written. Okay, yeah. So it's an OK lattice. OL is an OK lattice because we have seen that it has there's a K basis there's an element X in L, which is an OL, such that this is, actually I should be saying this is an OK basis of OL. Yeah. There's an element X in L such that its powers up to n-1, where n is the degree of L over K, form an OK basis of OL. And of course, this is a K basis of L as well. So the summary is that OL is an OK lattice in L. This is what we have. Yeah, see? Now, if here we had seen that every lattice has a complementary lattice. So what is the complementary lattice of OL? Well, let's denote it by CL over K. And it's called, so we have just given it a name, the complementary lattice of the lattice OK lattice OL is called the inverse different and denoted CL over K. So it's not a different, it's an inverse different. But in this very simple situation in which we are working, where P, K and L are P fields, every OK lattice is actually is one of these ideals. And as it's clear that this lattice OL itself is contained in this complementary lattice, so we have this n here is negative in the sense that n is, so this complementary lattice CL over K is either equal to OL itself or PL inverse or PL to the -2 and so on. See, the more or less the lattices, OK lattices in L are these ones on this side, and you have then PL inverse, PL to the -2, and so on. And this CL over K is one of these ones. Okay, that is the definition of the inverse different. It is the complementary lattice of the lattice OL. Okay, and then the different is defined to be the ideal. It should be OL, right? The ideal such that its inverse is the complementary lattice. So if it is the inverse of this is of course OL, the inverse of this is PL, the inverse of this is PL squared, and so on, right? So that is the different. It is an ideal of, so here's the summary. If you have a P field K and a finite separable extension L of K, then you have an ideal inside the ring of integers of L called the different of L over K. And the definition is, the characterization is that dl over K inverse is the complementary lattice of the OK lattice OL in L. Fine. So this is the definition, and it's a very important invariant of this extension L over K, right? The different of L over K. Good. Now, you consider a situation where you have a finite separable extension L over K and a finite separable extension M over L. Then you have this different of L over K and the different of M over L, and of course also the different of M over K. So how are these two things related to this? And the answer is that there's this transitivity. This can be called the transitivity relation. Transitivity says that the difference of M, the different of M over K is just the product of the different of M over L and the different of L over K. Okay, so normally this different of L over K, this is inside PL, right? But it is to be viewed as an ideal in, no, why am I saying PL? OL is what I want to say. It's an ideal in it's an OL, but ideals in OL will also be thought of as ideals in OM, right? You take a generator of that ideal as an OL ideal and let it generate an ideal inside OM, right? For example, I mean, this we already seen. Recall that the definition, more or less by definition, if I take the ideal PK and let it generate an ideal in OL, then what I get is PL and the exponent here is EL over K, more or less by definition. Okay, there's another way of saying that if I take a uniformizer of K and write it as unit times uniformizer of L to some power, that power is EL over K. So this relation and this relation are really basically the same. Because this pi k generates this pk. And this pi L generates this PL. Okay, fine. So let's prove this transitivity relation. So in proving it for the different is the same as proving it for the inverse difference. So for the complementary lattices, so it's enough to prove that Cm over K is equal to the product of Cm over L and Cl over K. Cl over K is to be viewed as a module in OM. It is, to begin with, it's a module in OL, and it has to be viewed as a module in OM. So one of the inclusions is clear from the transitivity of the trace, which we mentioned just now. So let's so we want to, what do we want to prove? We want to prove this inclusion. In order to prove this inclusion, I have to say that, to show that when I take the trace of this ideal here, when I take the trace, I'm inside the ring OK. SMK takes this ideal inside OK, and then it will have to be contained inside this, because that's the biggest thing whose trace isn't OK. Fine, so let's look at SMK of this, the product of these two ideals. But SMK is this composite, this and this. So I write it as SL over K followed by SM over L of this ideal. Now SM over L of CM over L, that is contained in OL more or less by definition of CM over L. And this inclusion follows from by the definition of the complementary ideal M over L. And okay, this CL over K, it's here. So it's CL over K. This CL over K, I've written it here because this trace M over L doesn't do anything to it really. So the whole thing becomes, it's at least contained in this SL over K of CL over K times OL, and that is by definition more or less contained in OK, by the definition of the complementary ideal here. So this inclusion is clear that CM over L times CL over K is contained in CM over K. Now I have to prove it in the other direction. So for the converse, what I have is, if I start with Cm over K, take the trace down to L, and then take the trace down to K, then of course I'll land into OK, because this here is equal to Sm over K. Fine. So because of this relation, what we have is that Sm over L of this thing here, this thing, is contained inside Cl over K. Now, this, I mean, you just need to figure out what is going on. And this can be translated as this statement here, and which amounts to this. And that, if you take it to the other side, comes to this. So the basic ingredients of the proof are that the trace is transitive. If I have M, L, and K, then I have the trace here, the trace here, and the trace here. And the trace here is the composite of this and this. That is the transitivity of the trace, and then the definition of the different. So there's that gives you the formula for these two things imply the formula for the transitivity the definition. I mean, that's not transitivity of the different. Okay. Now here is an important proposition, and the beauty of this proposition is that even if you don't remember how the trace is defined, you can sort of take this as how the different is defined. You can take it sort of as a definition, another definition of the different. So here is what it says. So remember the ring of integers OL, you have K is a P field, right? And L is a finite separable extension. Remember, then of course I have the ring of integers OK here and the ring of integers OL here. OL can be written as OK adjoint one element for some element in OL. So if I do it, and if I take the minimal polynomial of this alpha, then this f is of course an OK T, and I can look at f prime and evaluate it at alpha. This is not zero, I know, because f is a separable, right? It's a separable over k, so it's not a root of the derivative of its minimal polynomial. In any case, so this non-zero element generates an ideal. It's also an integer, I mean, right? Because the coefficients of f are integers and alpha is an algebraic integer. So the proposition says that the different of L over K is the ideal in OL generated by f prime of alpha. Now alpha could be any, you have a lot of choice for this alpha. So at the end, you get an ideal which is independent of alpha. All these f prime alpha for different alphas generate the same ideal. That's a corollary of this proposition. So let's prove that the ideal is basically it's saying that the ideal, the different as in is generated as an ideal by f prime of alpha for any alpha which such that OL is OK alpha and f is the minimal polynomial of that alpha. Okay, let's go to the proof. So let's define these elements bi's in OL by, I have this polynomial f of t. It is a root alpha inside OL. So I can divide it by t minus alpha. And I get some polynomial of degree t minus 1, of which the leading coefficient is equal to 1 because because f is monic, right? F is a minimal polynomial, so it's monic, and so I get these bi's, of which bn minus 1 is actually equal to 1. Now, the claim is that these bi's have been defined, and the claim is that when I take the basis dual to this basis, 1 alpha, etc., alpha to the n minus 1 is, of course, an OK basis of OL, right? That is given to us because OL is OK alpha. That's given. And hence, it's a K basis of L as well. Now let me look at, and I have this symmetric bilinear form, which is non-degenerate. So I can look at its dual basis, and the claim is that the dual basis is this one here, b naught up to bn minus 1. Well, I have not stopped any such thing. Okay, let's wait for a few minutes to see if I can reshare. Yeah, share the screen. Okay. Right. So there we are. Right. So the claim is that this is the basis dual to this basis. Let's prove the claim. So the minimal polynomial has exactly n roots in some algebraic closure. I don't care where it is. Then for every r in this interval 0 to n minus 1, you can check this identity. And this identity is true because if I take the left-hand side, the difference of the left-hand side and the right-hand side, if I take this difference, then it's going to be a polynomial of degree strictly less than n. It's a f already is a polynomial of degree n, and this, when I divide it by t minus alpha I get a polynomial of degree n minus 1. And when I take the difference with the right hand side, the r is between 0 and n minus 1. So the difference is also a polynomial of degree at most n minus 1. Anyway, it's strictly less than n. And it has all these n elements as roots. And therefore, this polynomial L minus R is identically 0, which is to say that L is equal to R. The left-hand side is equal to the right-hand side. Well. Can you still hear me?
Yes, sir. Yes, sir.
Yeah, okay. So let me try to share it again. I don't know. There seems to be some internet problem. What happened? Why is it not sharing? Why can't I see it? Just a moment. Let me try to. And this it's not. Yeah, okay. So maybe it's going to start again. Just wait. Yeah, it's a very bad internet connection. Well. So I've been disconnected from the iPad. So maybe I'll just, yeah, now just connected me again. Let's see. Start broadcast. Yeah, okay. Okay, yeah, so there we are. I mean, well, what was I saying? Yeah, I was saying that, yeah, we have proved this, and this can be written as the trace of this thing is equal to t to the r. Or in other words, it says that the trace of alpha to the I times beta j divided by f prime alpha is equal to 1 if I is equal to j, and it's equal to 0 if I is different from j. Okay? So this is what it means to say that this is the dual basis of this one. So these things, they constitute a basis which is dual to this given basis. Okay. So now we have just established one claim that we have found the dual basis. We have written OL as OK alpha. Then we get a basis 1 alpha to the n minus 1. This is an OK basis of OL. And we have found the dual basis, which is okay. So as this OL is this direct sum, our complementary ideal is going to be f prime alpha inverse times b, where b is generated by b naught, b1 up to bn minus 1, right? Because the dual basis was bi or bj rather divided by f prime of alpha. So the f prime of alpha is here now. Oh, this is terrible. This is, yeah. Let me try one last time and see if I can reconnect. Okay. So, yes. So we have found the complementary ideal. And if you want to say that the difference is generated by f prime of alpha, that is what you want to say, that the difference is f prime of alpha OL, then you have to show that this B is equal to OL. So that is what we need to show next, that this B, which is by definition the submodule generated by B naught, B1 up to Bn minus 1, is the same as the ring OL. And that is a simple computation because you have two different bases and you want to check that they generate the same submodule. If you can express one basis in terms of the other, then you have proved that they generate the same submodules. So here is a way of expressing these bn's in terms of these the powers of alpha. The powers of alpha is one of the, this can't be true here. I mean, it can't be a subscript. It has to be a superscript or something. It has to be an exponent. So don't take these formulae on trust. You just need to compute the beta j, the bj's in terms of the alpha I. And you will see that you are able to do it. And converse as well. We are able to express these alpha i's in terms of these beta j's. So they generate the same submodule. And that shows that this ideal B is equal to the ring OL, and therefore the inverse different, the inverse of the inverse different, gives you the different f prime of alpha.
Sir,
Yes.
hello, sir. It's the last term is a subscript n minus I plus 1. The subscript is correct, but it's a.
Yeah, so maybe it's a. You're right. Right. Yes. Then it's not not the exponent, but just a subscript. Fine. So let us summarize what we have done till now. We have a P field K, and we have finite separable extension of K. Then we have defined a certain ideal dL over K of OL called the different of L over K. And one of the ways of computing the different is that if I can write the ring of integers OL as OK alpha for some alpha in OL, and F is the minimal polynomial of this alpha, then the different is the polynomial F prime evaluated at alpha, and that generates the different L over K. Okay, so the reason I said this is nice is that it allows you to forget the other definition of the different in terms of traces and so on. You can just, for all practical purposes, you can just remember that if I write OL as OK alpha and I take F to be the minimal polynomial of alpha, then the different is the ideal generated by F prime of alpha. That's it. Now, in some sense, this different measures the ramification of L over K. You will say that, oh, there's already this E L over K, which measures the ramification. Yes, so this is a slightly different measure. So it's slightly, it's finer. The different is a finer measure because you could have two extensions L1 and L2, both extensions of K, and you can have EL1 over K equal to EL2 over K, but the different of L1 over K is different from the different of L2 over K. So that's possible. Not only is it possible, we'll come across many examples later. And in fact, those of you who are interested in doing computations, you can sort of look at, yes, so in order to understand these things, one has to compute it for various things. So Q2 has these extensions, right? Q2 root minus 3. So I'll just write the root minus 3 minus 1, root 3. Then you have root 2, root minus 6, root minus 2, root 6, right? So there are these 7 extensions and compute. So you have E equal to 2 for all of them, except for this. Here E is equal to 1 and F is equal to 2. But for these other 6 extensions, E is equal to 2 and F is equal to 1. What you need to compute is the different L over K for each of these L. L is one of these 7 extensions, 1, 2, 3, 4, 5, 6, 7. And K, of course, is Q2, and you need to compute what this is. So, for example, you'll need to compute OL. And then you'll need to write OL as OK alpha. Then find the minimal polynomial of alpha, and then compute F prime of alpha and let it generate an ideal. That's it. And what is it? Is it PL 1, 2, 3, whatever? So that is the important thing, right? That exponent. Fine. So now let's come to this theorem, which gives you some information about this exponent that I was talking about here, this exponent. So the situation is that you have a P field K, you have finite separable extension L of K, and you have the ramification index E L over K, the ramification index, and you have the different, which is some power of the unique maximal ideal of OL. That's the different. And the theorem says that the exponent of the different, S, maybe it should be called, sometimes we'll call it S L over K if you want to, mention which fields we are talking about. In any case, we'll just call it S in this theorem. It's equal to E minus 1 if and only if this E is prime to P. So it's, well, that's it. That's the first part of the theorem. There's more coming, but even this first part, recall that this condition E prime to P is the same as saying that L over K is tamely ramified. Okay, I'm just recalling the terminology. And in particular, I mean, E equal to 1 means that L over K is unramified. So that's in particular tamely ramified, and in that case, S is going to be E minus 1, which is 0. So part of the theorem says that the exponent of the different is equal to 0 if and only if L over K is unramified. Or, of course, this is the same as saying that this OL is equal to DL over K if and only if S is equal to 0, if and only if this L over K is unramified. Okay? And the second part of the theorem says that if this extension is wildly ramified, recall that if E is divisible by P, then we say that L over K is wildly ramified. So if L over K is wildly ramified, then the exponent of the different is goes from E. Here it was always E minus 1. If it is tamely ramified, but when it's wildly ramified, it's at least E and at most E minus 1 plus VL of E. What is VL of E? So VL is the valuation on L such that VL of L star is equal to Z. It's called the normalized valuation on L. And E is an element of L, right? I mean, E is in Z, so it is E is in OL, and therefore VL of E makes sense. So that is the second part of the theorem. It says that if L over K is wildly ramified, then the exponent of the different is between E, the ramification index, and E plus VL of E minus 1. It cannot be equal to this. So this VL of, if, for example, the characteristic of the field K itself is P, what we have is K is a P field. So what it means is that the characteristic of the residue field is equal to P. But the characteristic of the field itself may be P. There are two possibilities. I mean, it could be P or 0. So if the characteristic of K is equal to P, I mean, when it's P, it's the same as this P, the residual characteristic. So when the characteristic of K itself is P, then VL of P is plus infinity. So this theorem is saying that in that case, the exponent may be unbounded. And we'll see that actually, yes, there are extensions of degree P, for example, which have arbitrarily high exponents of the different. But when the characteristic of the field K is 0, then VL of P is just the ramification of index of E of L over QP. Right? VL of E is a ramification index of L over QP, hence a finite number. So in this case, there are only finitely many possibilities for S, for a fixed E, of course. If the ramification index is fixed, then the possibilities for the exponent of the different are only finitely many. Whereas if the characteristic of the field itself is P, then there are infinitely many possibilities. Okay, so let's prove this. So write OL as OK alpha just as just now, and we have seen that S is the valuation of F prime of alpha. This is what we have proved, because we have proved that DL over K is F prime of alpha OL. So this and this they are saying the same thing. So let's first consider the unramified case when S is equal to 0. So we have to prove that S is equal to 0 if and only if E is equal to 1. Oh, goodness. Now let me try again. Okay, so the unramified case, what I have to prove is that if E is equal to 1, the ramification index is 1, then the exponent of the different is 1. So this is exponent of the different is 0, sorry, which amounts to saying that the different dl over k is actually OL, if E is equal to 1. So if E is equal to 1, then the same as saying that L over K is unramified, right? Now, if it's unramified, then F prime of alpha is not going to be congruent to 0 modulo PL. Because, the alpha is, so F of alpha is going to be congruent to 0 modulo PL, of course, because F of alpha is actually equal to 0, and this alpha bar is non-zero. Goodness. You see, I have no solution to this except to keep on trying. Yeah, so I'm disconnected on the other device, and it's trying to connect. So let me try with this this thing here. Okay, so it has got connected, and let's see. No, it's trying. It's still trying. Okay, so this is going to be the last time. If it gets disconnected again, then we'll stop and we'll take it up on Wednesday. So this is the last time, huh? Okay. So let's go through it quickly. What happened? Why is it not showing the screen? You are sharing screen, but why is it not showing the screen? Okay, let's wait for a few minutes. Yeah, there's maybe there's some progress. Yes. Okay. Okay, so you write yes. So since alpha is separable over the residue field, f prime of alpha is not congruent to 0 mod PL. And that's the same as saying that f prime of alpha is a unit, so it generates the unit ideal, and that's the same as saying that S equal to 0. So now that we have taken care of the unramified case, what one can do by transitivity is that one just needs to look at the unramified case and the totally ramified case. It is not true that there are only two kinds of extensions, unramified extensions and totally ramified extensions. No, of course not. But if from these two cases you can recover the general case, which is that there'll be some ramification. I mean, the ramification index is going to be strictly great positive, and the residual degree is also going to be strictly positive. That mixed case, if you can reduce it to the totally ramified case and the unramified case, then you of course need to just consider these two cases. And that is possible here because of the transitivity formula for the different. Okay, so because of this transitivity formula, because if we know something about this and something about this, then we know something, whatever we need to know about this, it is enough to consider the unramified case, which we have already done. And now we have to look at what happens when you have a totally ramified extension, right? Every extension L over K of P fields can be split uniquely as an unramified extension followed by a totally ramified extension. So let's see what happens when L over K is totally ramified. Now, one thing we know about totally ramified extensions of some degree E is that the ring of integers OL is OK pi L for some uniformizer pi L of L. In fact, for every uniformizer. And then let's take the minimal polynomial of this pi L. It will look like AE t to the E, and AE is actually equal to 1 because the minimal polynomial is a monic polynomial, but I need to call it AE, and so on all the way up to A1t plus A0. So it's an element of OKT. You have this minimal polynomial. What we know is that this is an Eisenstein polynomial. So Vk of alpha I is strictly positive for all these i's from 0 to e minus 1, all these coefficients here. And Vk of alpha naught is actually equal to 1. This is not divisible by the square of a uniformizer. It's divisible by the uniformizer, but not by the square. The other coefficients, these ones may be divisible by an arbitrary power of a uniformizer. So anyway, here is our f, and this is Eisenstein. So we have these things, and if I write down f prime of alpha, I'll get this expression. It's a formal derivative. So f prime of t is e times ae t to the e minus 1 all the way up to a 2a2t plus A1. The A0 disappears, etc. So that's what I've written. F prime of alpha is this here. Now I have to, let's compute the valuation of each of these terms. The general term is something like this, right? The ith term is e minus I, a e minus I, and alpha to the power e minus I minus 1. So the valuation of this is, what is it going to be? Well, I've been calling it pi L sometimes, and alpha sometimes. So pi L is equal to alpha. Goodness. This is somewhat, so here, these are not alpha i's, but these are ai's. And this alpha is, so these are a's, that's fine. And this t should be alpha, right? Okay. So if I compute the valuation of this expression, so I'll have the valuation of the first thing, which is e minus I. It's in k. So whatever the valuation is, it's going to be congruent to 0 modulo e. Because remember, the thing is k star modulo O k star Vk is an isomorphism with Z, and this is contained in L star modulo OL star. Then I have VL, which is also an isomorphism with Z. And the coefficient here, which makes this diagram commute, is EL over K. So no matter which element I start with here I'll end up with something in EZ, right? E is short for EL over K. So this E minus I is in K, and this E minus I is also in K. So there VL is going to be congruent to 0 modulo E, and this is also congruent to 0 modulo E. What is this congruent to modulo E? That's the valuation of this last thing here. It should have been actually pi L to the E minus I minus 1. So the valuation of pi L is of course 1. So the valuation of this power is just equal to the exponent. And what is it congruent to modulo E? It's congruent to minus I minus 1 modulo E. And I goes from 0 to E minus 1. So the whole thing, this is congruent to 0, this is congruent to 0, this is congruent to minus I minus 1. So the whole thing is congruent to minus I minus 1 modulo E. Which means that in this expression, in this sum, in this expression for f prime of alpha, each of these things has different valuation. They have valuations which are different from each other, unless of course the term vanishes, in which case the valuation is plus infinity, right? So ignore the terms which vanish because they don't contribute anything to the sum. And now if I want to compute the valuation of f prime of alpha, that is the exponent of the different s, then if I have a sum of things, each of which has valuation different from the others, then the valuation of the sum is actually the infimum of the valuations, right? It's the infimum of the valuations. So this is equal to E minus 1 if and only if this E is prime to P. And when E is, so, I mean, it just comes by looking at this. And when E is divisible by P, the infimum can occur either at, the first term A1 or this term, it could occur at any of these terms, right? So the infimum occurs at the first term A1, then S is going to be equal to VL of A1, which is E times Vk of A1, but Vk of A1 is equal to 1, right? So this whole thing is actually equal to E, and in any case, what we want to say is that it's strictly greater than E minus. Or I should have written equal to E. Yeah, it's equal to E. If the infimum occurs at the last term, then this AE, of course, it is just the constant 1. And what is S going to be in that case? It's the valuation of this thing here. And that's E minus 1 because of this. And then VL of E, right? So that is the valuation when the infimum occurs at the last term. Otherwise, S lies somewhere in between. If the infimum occurs for some other value of I, then the infimum will lie somewhere in between these terms. So that proves the statement that the result is that the exponent of the different S is equal to E minus 1 if and only if E is prime to P and S lies in E and E plus VL of E if E is divisible by P. That was the statement which we have now proved. Now maybe this is a good time to mention this mass formula of SAR only in the tame case. The statement is the following: you take a K field, P field K, take an integer E, positive integer, and take TE of K to the set of all K isomorphism classes of totally ramified extensions of K of degree E, of course. So you look at the K isomorphism classes of all totally ramified extensions of K of degree E. And for each such extension, you have the different and you have the exponent of the different, and you define this Ck of L, this constant, to be this exponent of the different minus E minus 1. Now why this? In some sense, this exponent is equal to E minus 1 if it's tame. So this difference tells you sort of the deviation from tameness in general, right? We have seen that this S, the exponent is equal to E minus 1 if and only if E is prime to P, which is the same as saying, of course, that L over K is tamely ramified. And in this case, of course, this invariant Ck of L is equal to 0. In any case, what says mass formula says that when I take the sum over all L, remember this is the isomorphism classes or K isomorphism classes of totally ramified extensions of K of degree E, right? That's what this TE of K is. And for each such L, I have the group of automorphisms, and this is its order. I take 1 over that order, and I take Qk to the power minus CKL. Qk is of the cardinality of the residue field. And this formula says that when I take the sum over all such L, I get 1. Okay. Now it's a complete, it should be possible for us to prove this because we have done two things. We have classified, or rather, in fact, we have parametrized. That's a better word. We have parametrized this set T, E, K. And we have computed CKL for every L in this T, E, K. And therefore, it should be possible to just evaluate this sum, right? We know, not just that, we have computed not only CKL, but we have also computed CKL and ought KL as well. So everything entering in this formula has been explicitly computed. So that is the proof, in fact. In the case when E is prime to P, in the tame case, we have this constant is equal to 0. We have seen this because the S is equal to E minus 1. And therefore, S minus E minus 1 is 0. We have computed the group of automorphisms. And it is cyclic of order G, where G is the GCD of E and QK minus 1. That it's cyclic we are not going to use. We just need to know that it's of order G. And we have also computed, parameterized this set. And we had seen that there are exactly G elements in this set. So the sum becomes, what? 1 over G, QK to the 0, L, and there are G such L's. So this will be G times 1 over G, and that's equal to 1, right? That's what becomes this mass formula. It's more difficult when you have wild ramification. Okay, so in the 15 minutes which remain, let me quickly recall or define the discriminant. What we have defined till now is the different. And now we come to the discriminant. So again, let's take K to be any field for some time, and you take any finite separable extension. When I take a basis, K basis of L, I can define the discriminant of the basis. That's the discriminant of that basis to be the determinant of the matrix whose entries are the traces of Bi times Bj. The Ij entry is the trace of Bi times Bj, right? That gives me a matrix, and I just take the determinant, and that determinant is not 0 because, again, this trace map is, it's a non-degenerate bilinear form, and therefore the determinant of its matrix is not 0. It's non-degenerate bilinear because the extension is separable. Okay, now let's see what happens if we, so that's the determinant of a discriminant rather of a basis. Oh goodness, no. Okay, that was when we chose a basis. What happens if we choose a different basis, C1 to Cn? Then there's going to be a change of basis matrix, M, some change of basis matrix, which will express the new basis in terms of the old basis. And one can check that the discriminant of the new basis differs from the discriminant of the old basis by the square of the determinant of the change of basis matrix M. It differs from each other. These things differ by the square of the determinant of the change of basis matrix. And moreover, so that's one thing. And in particular, if I take my this basis, okay, so right now I'm working with an arbitrary field. So there's no distinguished ring inside those fields. So I have one more thing to say about this general situation. That is that I can take the dual basis with respect to this bilinear form. And of course, then I have the discriminant of the dual basis as well. And the thing is that you can verify that the product of the discriminant of the given basis and the discriminant of the dual basis is 1. Okay. So now let's come back to, it's taking some time. Let's come back to our P field K. And if I take an OK lattice, then I can take a basis, 2 bases of this OK lattice. Then of course the determinant of the change of basis matrix will be a unit in the ring of integers, because both M and M inverse have entries in OK. So the determinant is invertible because the matrix is invertible, right? And therefore the ideal generated by this discriminant of this basis will depend only on lambda. It will not depend on the basis. It will depend only on the lattice of which it is a basis. And this other relation that we had, that if I take the discriminant of a basis and the discriminant of the dual basis, the product is equal to 1, will translate into this formula, that if I take the discriminant ideal of a lattice and the discriminant ideal of the complementary lattice, the product of these two ideals is the unit ideal. And it follows from this relation, as I said. Okay, so the definition is that the discriminant of L over K of this extension of p-adic fields, this is not an extension, this is not the notion of discriminant for an arbitrary extension of fields. It's the notion of the discriminant for an extension of p-adic fields, or p fields as I've been calling them. The discriminant is the ideal generated by the discriminant of any basis, where I take a basis of the ring of integers OL as an OK module. So the discriminant ideal is going to be the maximal ideal to some exponent dl over k, and that exponent is of course called the exponent of the discriminant of L over K. So now if I have the same situation, finite, I have a P field K, I have a finite separable extension L, then I have various invariants attached to this situation. I have the degree of the extension, I have the ramification index, I have the residual degree, and of course I have the formula which says that the degree is the product of the ramification index and the residual degree. But now today, we have also defined the exponent of the different and the exponent of the discriminant. We have defined these two things today. So as we saw, these three things are connected, right? This is the are there any relations between all these things? That's what the next proposition says, that the exponent of the discriminant is the product of the exponent of the different and the residual degree. That's the proposition. Let's prove this. So let's take a basis, OK basis of OL, and let's take a uniformizer of L. Then, by definition, this, pi L to the minus S times B1, and so on up to pi L to the minus S Bn, that is an OK basis of the complementary ideal of the different, right? Because this S is the exponent of the different. So in some sense, the exponent of the complementary ideal is minus S. So when I multiply by pi L to the minus S, I get a basis of the complementary ideal of the different. Now, if I take the change of basis matrix, change of basis from where to where? So I have this, so that's one basis of L over K, and this is another basis of L over K. And they have to differ by, so if M is a change of basis matrix, then this discriminant differs from this discriminant by the square of this matrix. So the delta of C, the discriminant of this lattice C will be the square of M multiplied with the discriminant of OL, which I've been calling now the discriminant of L over K, right? But the discriminant of the complementary lattice is the inverse of the discriminant of L over K, because this has the dual basis, right? So the discriminant of a basis and of the dual basis, when multiplied, give you 1. So that gives you that M is, and also M is equal to this because the norm of pi L is pi K to the power F. This is the residual degree. So these two relations, when I put them back into the formula star, this was the formula star here, I get this here, which can be rewritten as saying that the exponent of the discriminant is the exponent of the different times the residual degree. So I've gone through this rather quickly. I mean, you can take a look at it yourselves because I wanted to finish before the next internet failure. I'm sorry we have to put up with this. The only thing I can offer is that if there's something which was not clear, you can always write to me, send me an email, and I'll try to answer your questions. Okay, so are there any questions today? Yeah, if not, I'll sort of stop here and we'll meet day after tomorrow.